Hi, my name is Will Crawsick, Scientific Services Manager at Chemical Computing Group. Today I'd like to demonstrate the tools that we have in Mo for fragment-based drug design. In today's session we're going to be using scaffold replacement to generate some fused rings, and in the process a substantially different scaffold for our ligand. So let's get started. So I'm just going to go ahead and use the open button to retrieve the file that we're going to be working on today. So I'll select the file, click OK, and I'm greeted with this Load PDB file panel. This allows me to select what data we're going to load into Mo, and here I'll accept the defaults, which loads in the structure of human P38 MAP kinase. Notice that it's coloured by secondary structures. So here we've got the beta sheets in yellow, helices in red, and turns shown in blue. Now, before we can start thinking about fragment-based drug design, the very first thing we need to do is prepare this model. This is a raw PDB file, so typically it won't have any hydrogens or charges included. Perhaps it's also got some missing loops. So for that, I'm going to use QuickPrep, our automated preparation wizard, which comprises three main sections. The first handling the preparation and cleanup of the structure. Second sets tethers and restraints. The third handles refinement. Again, sensible defaults have been selected for the majority of use cases. This panel is no exception. I don't need to make any changes. I'll just click OK to start that calculation, and I get a progress update at the top left of the main Mo window. Now, I'd just like to take a moment to explain what's going on in the background here. So the first preparation stage ensures that we've got a complete model. What we're doing here is adding in any missing hydrogens, charges, and side chains. We'll also add in any missing loops from our model, up to 10 residues in length. Protonate 3D optimizes the ionization states of the bound molecules and their side chains. It also generates a hydrogen bonding network through the placement of polar hydrogens. By default, we'll tether any atoms within the active site, and the reason that we do that is to ensure that we can retain the original geometries of those atoms as captured by crystallography. We don't want to lose those geometries to processes such as energy minimization. Likewise, we can fix any atoms that fall outside of the active site, and we can do that for reasons of computational efficiency. The final refinement step performs an energy minimization to ensure that we don't have any clashes in our structure. So I see the message has gone from the top left of the main Mo window. It tells me that we've got a prepared model. So with that, I'll cancel that panel. And next, what I'd like to do is get familiar with this ligand and how it's interacting with the receptor environment. So to get a better view of that, I'm going to hit Site View. That isolates the ligand together with any residue within 4.5 angstroms. And next, I'd like to manage all of the data that we have in our system. So I'm going to open the System Manager, and I'm going to pin the System Manager to the main Mo window. As I say, this will allow me to control the data that we have in our system. So from here, I can hide and show different atom sets. I can make selections, I can render, and I can also generate surfaces. So in this case, I'm going to use the System Manager to render our system by first hiding the ribbon, and second, I'm going to render the ligand a bright color. So there is our prepared model. So next, we can now think about fragment-based drug design. So I'll just go ahead and open the panel, and within this menu, you'll actually notice that we've got 7 different operations, and these all point to the same unified panel. So I'm going to select the Scaffold Replacement operation, which opens up our panel comprising 4 main sections. The first allows us to define the system in terms of both the ligand and our receptor. The second part of the panel allows us to select which operation we'd like to perform, and you'll notice here these options were the same that we saw earlier within the compute pull-down. The third part of the panel allows for filtering and adding in pharmacophores, and the fourth and final allows for refinement and scoring. So I'm just going to move this panel to one side, and now we're going to set up for our scaffold replacement operation. In this, we'll be generating new ligands by replacing a portion of the ligand whilst preserving a portion of the remaining chemical groups. And here, the panel is actually guiding me what to do next. So it's saying select the heavy atoms of the scaffold that you'd like to replace. Now I find the most convenient way to select these atoms would be to click on the 2D button, which opens a 2D schematic of our ligand. And that would allow me to simply drag a selection box over the atoms that I'd like to replace. In a previous example, we used the scaffold replacement operation to replace quite a large portion of the scaffold. But we can also use it to replace a focused portion of the scaffold too. So here I can see that we've got potential to form a fused ring. And if we did, that's going to offer a substantially different scaffold to our starting ligand. In the main Mo window, we see that the atoms that we've selected are highlighted with this green halo. You'll also notice the green arrows showing us the attachment points. So if I go back to the panel, you'll see that that information appears here as well, showing us that we've selected 5 atoms and we've got our 3 exit vectors. But next, given that we're going to be generating a fused ring, we need to remember that Mo would like to avoid generating intraligand clashes when generating novel scaffolds. In this case, we want that to happen because we want to generate a fused ring. So for that reason, I'm going to click on the gear wheel to go into the settings, and I'm going to manually push up these clash energies up to 10, and I'll click OK just to allow Mo to generate that fused ring, which is typically avoided since the system wants to avoid generating intraligand clashes. As I say, in this case, I want that to happen. Next, if I go down the panel, I see that some default descriptor filters have been added. We've got a molecular weight cutoff, a TPSA range, and a note on reactivity. I also notice that this check filters button is coloured red, and if I just hover my mouse over there to raise bubble help, it says this button is coloured red if the ligands do not pass the descriptor filter. So I can click on this button to give me further information, and here it says the molecular weight cutoff of our the molecular weight of our ligand is 528. Now, the reason that might be a problem is because you'll remember that the molecular weight cutoff was 500. So this is saying that this current ligand would not pass that filter. In this case, we actually want to add some atoms, so we're going to be increasing the molecular weight. So we need to think about changing that. So for that reason, I can just manually push that up. So I'll push it up to 600. And with that, I can initiate our run by clicking search. So Mo is now searching for scaffolds that are going to replace the atoms in the halo between the bond vectors. And because we've allowed intraligand clashes, I'd hope to see some fused rings in our results database. In the background, Mo is searching a fragment linker database which contains just over 40,000 entries. We do have access to larger databases if we need. So here I see that results are being written to the database viewer. This is the format that we use for storing database entries, or in this case, results. It looks and feels much like an Excel spreadsheet, but if I drag the mol field open, you see that it actually contains the 3D structure of our ligands. Within here, we also have some relevant data in terms of quantitative output for the ligands that have been generated, including a prediction on the ease of synthesis, together with the linkers that have been used to generate these structures. The database viewer would also be our launching point to various tools that we have in Mo. So for example, here we could jump into QSAR if we wanted to. In this case, though, I can use the database viewer to peruse the results of the novel scaffolds that have been generated. And I can also use it to launch a browser. So this is going to allow me to view the structure of our newly generated ligands, both in 2D format here, together with the 3D format in the 3D window there. So if I just move that to one side, I'll just hide the 2D schematic and click into space there to deselect the atoms. And here we see our newly generated scaffold shown in green against the original co-crystal ligand shown in orange. Within the database browser, I can add in different fields from the database viewer. So, for example, if I wanted to write the RMSD to this browser, I can do that. Perhaps I want to add rsynth, also a predictor on the ease of synthesis. This is on a scale of 0 to 1, whereby 0 would mean that it's not likely to be synthesizable, whereas 1 means it's likely to be easily synthesizable. Those values are also written to the top left of the main Mo window. And from here, I can click through to view these one at a time, or perhaps what I can do is just click to autoplay and have a look at some of those scaffolds that we've generated. Here we see that we have indeed generated some fused ring conformations, allowing us to substantially change the scaffold, which increases chemical diversity, but also improves the rigidity of our ligand. In today's session, we use the scaffold replacement operation to generate novel scaffolds featuring a fused ring. We customize the default filters to provide us appropriate structures, which could be minimized and scored in the receptor environment. I hope you've learned a lot today. If you have any questions, please reach out to me at support@chemcomp.com.